We can't build the Saturn V rocket anymore because we lost the blueprints. You've probably heard this story before. Somewhere between the moon landings and today, humanity supposedly misplaced the instructions for the most powerful rocket engine ever built. But that's not actually true. The blueprints still exist. They're sitting in filing cabinets at NASA's Marshall Space Flight Center. What we really lost was something much harder to replace: the people, the machinists, the welders, the engineers who carried thousands of tiny manufacturing tricks inside their heads. Because the F-1 rocket engine wasn't built like modern machines. It was handcrafted at industrial scale. And here's the part almost nobody talks about. The F-1 wasn't the end of rocket engineering. It was the beginning. NASA actually built engines that were more powerful, more efficient, and dramatically cheaper. They tested them, proved them, then buried them. Not because they failed, because they were too efficient for the system funding them. One F-1 engine produced 1.5 million pounds of thrust. 5 together generated enough force to lift the Saturn V moon rocket off the ground. To understand how insane that really is, imagine strapping the power of an entire small city underneath a metal tube filled with fuel and trying to keep it from exploding. Because that's exactly what engineers were doing. The F-1 engine burned something called Rocket Propellant 1, or RP-1, an extremely refined kerosene, together with liquid oxygen. Inside the combustion chamber, temperatures reached nearly 6,000 degrees Fahrenheit. That's hotter than lava, hot enough to melt steel almost instantly. So here's the obvious question. How do you stop the engine from melting itself apart? The answer is one of the cleverest tricks in engineering. Before the fuel ever reached the fire, it was pumped through 178 tiny tubes wrapped around the engine walls. Think about wearing a jacket filled with ice water pipes while standing inside a furnace. That's basically what the engine was doing. The fuel absorbed heat from the walls first, keeping the metal cool enough to survive. Then the fuel entered the combustion chamber already preheated, which made it burn even more efficiently. But heat wasn't the biggest problem. Sound was. Early F-1 tests kept exploding. Not because the fuel mixture was wrong, because pressure waves inside the chamber started bouncing around like echoes in a cave. Imagine blowing air across the top of a bottle. Now imagine that vibration becoming so violent it tears the bottle apart. That's what was happening inside the engine. Engineers called it combustion instability. The engine literally shook itself to death in milliseconds. The explosions were happening so fast that cameras recording the tests sometimes couldn't even capture the failure before the engine disappeared. NASA eventually solved the problem with something unbelievably simple: tiny copper barriers called baffles. Basically, speed bumps for fire. They disrupted the pressure waves before they could grow strong enough to destroy the engine. That tiny change transformed the F-1 from a bomb into the most powerful operational rocket engine in human history. But the real monster inside the engine wasn't the combustion chamber. It was the turbopump. The turbopump was the heart of the F-1. Its job was simple: force massive amounts of fuel and liquid oxygen into the engine fast enough to maintain combustion. Simple concept, absolutely horrifying engineering. The turbopump spun at over 5,000 revolutions per minute while moving fuel at a rate so extreme the engine could drain an Olympic swimming pool in under a minute. Imagine a fire hose powerful enough to empty a swimming pool while spinning like a jet turbine. Now imagine that machine operating beside liquid oxygen, cold enough to freeze metal. Here's where physics became dangerous. When liquid oxygen moves too fast, pressure drops. And when pressure drops, the liquid starts boiling. Tiny bubbles form inside the pump. This is called cavitation. Those bubbles collapse violently against the metal blades like microscopic explosions. Over time, they can literally shred machinery apart from the inside. NASA solved this using something called an inducer, a spiral-shaped section at the front of the pump that compressed the liquid oxygen before it entered the main system. Think of it like slowly guiding traffic into a tunnel instead of letting thousands of cars slam into the entrance at once. Even today, aerospace engineers still study the F-1 turbopump because some parts of its reliability remain almost unbelievable by modern standards. And here's the important part. The F-1 only needed to survive once. The engine was expendable. It launched, reached space, then fell into the ocean. That allowed engineers to push materials right to the edge of destruction. Modern reusable engines can't take those same risks. They need huge safety margins. The F1 was basically engineered like a drag racing engine. Maximum power, minimal concern for long-term survival. But then something strange happened. NASA built engines even better than the F1, and instead of using them, they buried them. One of those engines was called the F1A. This wasn't a prototype, it was a fully developed upgrade. More thrust, simpler components, better reliability, about 20% more powerful than the original F1. And then Saturn V production ended. The hardware didn't explode. The program didn't fail. The engines were simply placed into storage. Then NASA shifted toward the space shuttle program. And this is where rocket engineering changed completely. The new engines used liquid hydrogen instead of kerosene. Hydrogen engines are incredibly efficient, but also dramatically more complicated. They require enormous fuel tanks, extreme insulation, complex plumbing, higher costs, more contractors, more infrastructure. And complexity attracts funding. The next generation engines NASA buried were often cheaper, simpler, and easier to manufacture than the systems that replaced them. One engine in particular shocked engineers, the TR-106. Unlike the F1's complicated injector system containing thousands of tiny holes, the TR-106 used something called a pintle injector. Think of a shower head versus a garden hose nozzle. The F1 was the shower head. The TR-106 was the adjustable hose. Simpler, cleaner, more stable. During testing, engineers reportedly threw objects into the combustion flow to see if they could destabilize the engine. It kept running. That's how stable the design was. Then came the RS-84. This engine was supposed to combine the raw power of the F1 with modern reusable efficiency. It used oxygen-rich staged combustion, one of the hardest rocket engine cycles on Earth. Imagine a car engine that recycles its own exhaust to create even more power instead of wasting it. That's basically what staged combustion does. NASA tested it, validated it, then canceled it. Not because it failed, because budgets changed, mission priorities shifted, and simpler engines often don't create the same funding ecosystem as giant, complex programs. The craziest part? Some RS-84 technical details are still restricted today, even though the program itself was canceled decades ago. So no, we didn't lose the ability to build the Saturn V. We lost something stranger: the willingness to build machines that were simple, brutally powerful, and efficient. The F1 wasn't the end of rocket engineering. It was the beginning of a future we decided not to continue. And maybe that's the most unsettling part of all. Some of the greatest engines humanity ever created didn't fail. They were abandoned. If you want more hidden engineering stories like this, the machines, physics, failures, and inventions most people never hear about, subscribe right now. Because once you start looking underneath modern technology, you realize history is full of incredible machines we quietly left behind.